this is the general setup we're going to use for this weather station for the solar tree. There's a weather station setup from SparkFun, plus this sensor here, which does pressure and temperature. And all of those sensors are going to be read by an Arduino Pro Mini. And then the Arduino Pro Mini will report to a Raspberry Pi in order to actually record whatever the weather data happens to be. Now, exactly what that data is, well, we have rain accumulation from the sensor here, wind direction from a weather vane, and then wind speed from an anemometer. This here is a BMP 388 temperature and pressure sensor. The sensor itself is made by Bosch, and then the board is from a company called DF Robot. Now, the reason for having this Arduino in the first place, rather than just connecting all these sensors to the Raspberry Pi, that is something that you could do. The reason for having the Arduino is the weather vane here works a little bit differently. It requires an analog to digital converter on the Arduino, and actually that was the reason for using the Arduino here instead of just the Raspberry Pi. The Raspberry Pi doesn't have any ADCs on board. We needed...
What is an analog input?
Well, you've kind of given it away a little bit, haven't you? Analog to digital converter is what that stands for. I should also introduce the guest here. I have my dad here just as somebody to explain this to, because I tried explaining a program to the wall and it did not work very well. So I have an actual person so that we can have a video that's hopefully actually useful. I guess the next part of this process is that the rain gauge and the anemometer are connected to interrupt pins on the Arduino. And the reason for that is we don't want to continually ask the rain gauge and the anemometer, have you completed a rotation or have you tipped back and forth? We want those sensors to tell us when an event occurs, and that's what the interrupt pins let us do. That's these three sensors, and then the temperature and pressure sensor, that communicates by SPI, Serial Peripheral Interface, if I remember correctly. And that means that, well, you just talk to it digitally, ask it for data using the commands that it understands, and that whole process is handled by the existing Arduino code that makes it easy to use this sensor. The Arduino is sitting here reading these things, and, well, that's not very helpful because the data isn't going anywhere. So the next step is, how do we get data into the Raspberry Pi? Well, I don't have it drawn exactly, but a company called FTDI makes USB to UART converter chips. So you plug that into the USB port here, the other side goes to the Arduino over here, and it presents itself as if it was an old-fashioned serial port. And the Arduino is programmed such that if you send it any single character over serial, I've gone with a question mark because we're asking for data, send it any single character and it will reply with all of the latest data. Now, the other reason for doing that method rather than having the Arduino report data every 5 minutes or 10 minutes or something is this makes it a little bit easier to adjust how often we ask for data. You would either need to have some method of more complicated commands going back and forth between the Arduino and Raspberry Pi, or you'd need to just reprogram the Arduino in order to change the data interval. So when the Arduino replies, it sends all of the data it's been collecting as text, and it sends them separated with commas. That way, the Raspberry Pi can just take the incoming string of text and save it to a file with the CSV extension, comma-separated values. And from there, you can open it in Excel or whatever, and do whatever sort of processing you like. MATLAB, perhaps, if you want to do something fancier.
So is the Raspberry Pi more powerful than an Arduino?
Yes. And I laugh because he knows that. Yes, the Raspberry Pi is considerably more powerful than the Arduino. And the reason for having the Raspberry Pi involved with this at all is because eventually the Raspberry Pi will also be doing some other stuff for the solar tree. For now, it's just running the weather station, but we're going to need the extra computing power for stuff down the line, and that's why we added it at this stage. So that's generally how the hardware is set up. I think it would also be good to show a little bit of how those sensors actually work. This is the data sheet for that weather station, and they show the rain meter here. The anemometer works exactly the same. Basically what they're showing is that you need to add a decoupling capacitor and a pull-up resistor to the rain counts or anemometer output. Now, I actually ended up going with a much larger capacitor, 10 microfarad instead of 10 picofarad, and I'll show why in a moment. That said, I think you could actually get away with a considerably smaller capacitor. On the other hand, 10 picofarad strikes me as low. I haven't really experimented with that because 10 microfarads work just fine. I also actually omitted this pull-up resistor in favor of just using the internal pull-up resistor on the Arduino. There's a command that you can run when the Arduino starts up, which essentially enables a resistor as a pull-up just like this, except that it's inside the chip, and well, the good thing is now you don't need to worry about it. It's one less part that you need to put on any printed circuit board you make.
So you get a high or a low pulse every time the rain bucket dumps?
Exactly. So what's, I thought I had one open. Okay, I don't have it open. But I can show the read switch. This is how the rain bucket and the anemometer know that something has happened. There's a little glass tube with two pieces of metal inside, and when you put a magnet near it, they either touch when the magnet's close or they spread apart when the magnet is not close. And every time the rain bucket tips back and forth, you'll get one pulse on this pin here, the rain count pin as they've called it. And then likewise for the anemometer. Every time it turns around once, you'll get one pulse on the anemometer output pin. The weather vane is a lot harder to explain, at least when you look at it like this. What's going on is that, just like the other two sensors, there's a magnet which causes these read switches to close when it goes by. That view of it is a little bit misleading, so I made this in order to hopefully make it a little bit clearer. So what happens is that at any given moment, either one or two switches are closed. So there's 8 resistors for north, south, east, west, northeast, northwest, southeast, southwest. And then you get one more, even more intermediate direction, north, northwest, south, southeast, and so forth. And you get those by having 2 of the switches closed simultaneously. So, yes, that's exactly what I thought when I first saw that. That's how it was done. So, as the weather vane rotates, this is the sort of pattern you'll get. Now, these resistors aren't actually in any particular location. I didn't try to match them to the pattern, to their physical arrangement, but this should give the point I'm trying to make of how the weather vane works. Now, you'll also see that this voltage was changing as I was opening and closing the switches. Each single switch or each pair will give a different voltage, and because of that we can differentiate between all the different positions. I was hoping that they would all map cleanly, making it a very easy thing to deal with, so that, like, how do I say it? So there's 16 directions that we want to account for, these directions here. I was hoping that they would, you'd basically just take the 0 to 5 volts, divide it by 16, and
go around the compass.
Exactly. It's not quite that simple because these resistances are not, they do not result in nice even 16ths of the 5 volts. So you end up with really weird ranges or step sizes that you need to account for. So what I've done here, this is for calculating what voltages we need to detect on the anemometer. Not the anemometer, the weather vane. And all of it assumes a 10K resistor, which is exactly the same as the datasheet assumed that we would use. So the first thing to do is calculate the resulting voltage drop, or output voltage if you prefer to think of it that way. And then to calculate what would the ADC output in order to represent this voltage. So basically you're taking the range 0 to 5 volts and mapping it to 0 to 1023. And, well, this is the formula that does that if you want to try and work that backwards in Excel language. Or if you've worked with ADCs, you'll go, oh yeah, I know that. The next thing is that these resistor values are not going to be exactly whatever they say they are. There's going to be some amount of tolerance to it. And you could do a little more thorough tolerancing than I've done, but what I've done seems to work, so I'm going to go with it. And what I have done is, well, the first thing was to declare, okay, what will our tolerance be? And I started with 5%, which is a typical tolerance for resistors. So 66 counts is nominal, so minus 5% is 63, plus 5% is 69. And this range over here, I just wanted to know how many counts of tolerance do we actually end up with. We don't actually use this. This was just more for me to try and get a feeling for what's going on. The important part is this error versus no error column. I'll start with these values here. What this is telling us is that this range does not overlap with this range, and that is explained by this no error message here. This one says error, and the reason it says error is because 80 to 88 overlaps with 88 to 98. This value is repeated, which means that if we read a value of 88, we actually can't determine if it's east-northeast or just east. And just by playing with it, plugging in different numbers, I found that 2.4% was the largest value that gave me no error for all of these columns, all of these rows. So another thing to note, I did this as a table so that you could sort by direction or something like that. The error, no error stuff will break under any condition except where you sort by output voltage ascending. Just a quirk of how I had to do the equations. So that's how I calculated what voltages and, more importantly, what ADC values we need to watch for on the weather vane. So what do you think I should show next? Should I show code next, or should I show it running?
Show it running. I think that'd be
okay. So
to see.
Now that you've... Oh, I forgot something. There is one more thing about the hardware that I should show, and it is... Let's go back to the... Here it is. The datasheet here shows the capacitor on the rain count and the anemometer outputs. The reason that is so important is because this is the switching waveform we get without the capacitor. So if we have this setup here, but no capacitor, you end up seeing the reed switch bouncing. And you also get these nasty undershoots. They're probably not going to cause problems, but it's good to avoid those when you can because they might actually damage a more sensitive microcontroller.
What is the duration of the bounces there?
Well, we're at 5 microseconds per division. So the largest bounce is, looks like 12 microseconds. So when the rain gauge and the anemometer are not triggering, they're idling up at 5 volts. And when the event occurs, when the rain bucket tips or the anemometer rotates, drops down to 0. And then either based on the springiness of the contacts or some fluke of how the magnetic field works, I don't know exactly, and it doesn't matter, the contacts end up bouncing and we get these extra pulses. And this one happens to be large enough to register as a second pulse. And we actually got the same effect with just different timing on both the anemometer and on the rain gauge. So if you stick the capacitor on, those go away. You get a nice, smooth decrease to 0 volts, and then it just stays there, which is exactly what we need. And it stays there. Of course, it will eventually rise back up when the pulse is complete, but it will do it exactly the same as this. It'll be a nice, continuous slope from one voltage to the other. So I think that's the last thing to say about how the hardware works, and now I'll show how the program runs. All right, so there's 2 programs here. There's one, which runs on the Arduino, and we'll go through that in a bit. And then there's this other shorter program, which runs on the monitoring device, and it's written in Python. Because
That's
it's in
the Raspberry Pi.
Yes, because it's written in Python, this program with one change, this here, you can run it on a Mac or Windows or any version of Linux. Python is just, well, it's just really good for that sort of thing. Let's see. So This is the Arduino code's already running, so we're going to get this program running, and you'll be able to see what it's doing. There's actually a second thing that I'll pull up here, which is this folder, and it has the Python program, the Arduino program, and once I start this program, we're also going to see another file appear, the weather data. So run. Now the first thing it does is it prints the path to where we're saving data. And you'll notice we now have this extra weather data CSV file. There's a couple extra spots where it prints the date and time. I could make the program get rid of them, but it's just extra complexity, and I don't think it's worth it. After that, it prints these two lines, which come from the Arduino and identify the program that is on the Arduino, and then this here is explaining how to make the Arduino do something. So after the Arduino tells you all about itself, it sends this line just once. And what this line is once it gets written into the CSV file, this ends up working as headers for the various columns of data. And then this, of course, is the data that we're putting into those columns. So rainfall in inches, average wind speed in miles per hour, gust wind speed miles per hour. This one's kind of for diagnostics. It's the wind ADC counts, as I called it. In other words, it is the analog to digital converter reading that we just spent a bunch of time talking about for the weather vane. Say again?
The raw reading.
Exactly. It's the raw reading from the ADC. And this is the direction that the Arduino decided the weather vane is probably pointing based on this value. And I'm printing both of them because there's a certain condition where this might actually end up being blank. And if that ends up being blank, I want to know why did it end up being blank. In other words, what value did we get here from the ADC that resulted in a blank? The next thing is temperature in degrees centigrade. That's just the native value that the temperature sensor puts out, and there's no reason to incur extra error by converting to Fahrenheit or anything else. And then same deal here. This is barometric pressure in pascals. I left it as is, again, because, well, there's no reason to convert it and lose precision. This is another value which I send sort of as diagnostic. What it is doing is, it is the time in milliseconds since we last requested data. See, 03, 05, 07, we're asking for data just about every 2 seconds, and happens to be just about 1990 something milliseconds. It's always a little bit quick according to the Arduino. And I'm printing this just as basically a reassurance to know that the Arduino is still cycling through properly and calculating data over the correct interval. So that's all the data that this is sending, and
It's putting that into a file somewhere.
exactly, it's putting it into a CSV file. You can actually, it's not quite live. This updates, I don't know, every once in a while, basically. macOS will update this little preview thing. But if I stopped it, I could open the file in Excel and see all the data in your more typical way. But yes, it's putting it into a CSV, and now you can see it with the headers in the right spots. So that's how that works. I might actually split it so that there's another comma here. I don't know, just possibly another way to do it. So the next thing to show is, let's have these numbers actually change. Because I have all this set up next to me, I can just play with the sensors and make the readings change. So the first thing is I'm going to take this leftmost reading, the rain gauge, and we're going to make it think it's raining. So I'm just tipping it back and forth now, and any second you should see the readings start to come in. And it's raining. And it's raining, I don't know, 0.6 or 0.7 inches, sorry, 0.06 or 0.07 every 2 seconds. That's a lot of rain. Next is average wind speed in miles per hour. So we'll give the weather vane a bit of a flick, not the weather vane, the anemometer. And the way this works is every time the Arduino sends a reading, it resets a timer, and it uses that timer for calculating the average wind speed over the time since it was last asked for data. So if I'm asking for data once every 10 minutes, we get the wind speed average over that 10 minutes. The next value is the gust wind speed, again, over the duration since we last asked for data. So that is the single fastest rotation of the anemometer since the last time we asked for data. And that gets reset every time we ask for data. We reset assuming that there won't be any rotation, so the gust wind speed goes to 0, average wind speed goes to 0, but of course they both count to the appropriate value as the next time it goes around. Now what else is there? I can turn the weather vane's been pointing northwest all this time, so now it should be pointing just about straight north. There you go, north. Should be something like northeast. Yep, northeast and east. And let's see if we can get south-southwest, or south-southeast. All right, whatever. There you go, south-southeast. And that there is your temperature, so I can warm up the temperature sensor, and any second you'll see the temperature start to go up. There you go, a little bit up, 25 from 24. And there's nothing I can do to increase pressure, so I can't really demonstrate that that's doing anything. But according to me checking online conversions, that does actually seem like a plausible value. So yeah, that's the program running. So I'll stop that, and I'll open this in Excel. So here's the data as you would see it in Excel, and then somewhere down the bottom here we'll have the ones where stuff actually changed. There you go. And yeah, that's what it'll look like in Excel. Of course, once we actually have this installed for real, we won't be collecting data once every 2 seconds. It'll be every 10 minutes or something like that.
And you can change how frequently it updates.
Exactly. You can control that on the Python side. So basically what I'm thinking is that if you start getting a whole lot of rainfall or the wind speed is picking up, Python might monitor that and increase the data collection rate in order to improve the, basically to get better gust wind speed readings. Actually, I guess you would sort of already have an indication of how much the wind speed is changing based on the difference between gust wind speed and average wind speed. If they're very close, the wind's real consistent. If they're far apart, not very consistent. But yeah, the fact that Python can change the averaging interval simply by asking for data at a different interval, I thought that might be real helpful. What do you think, Python first or Arduino first?
I think Arduino first.
That's what I was thinking. Okay, so there's a lot going on here at first. The main loop is pretty straightforward. There's a whole lot of variables for just tracking everything that's going on, but again, it all ends up actually seeming fairly simple by the end of it. Remember, I was talking about how we need to keep track of time. That's what this is doing. We need to keep track of the text that comes in over serial. We don't actually need to use it for anything. We just need to put it somewhere in order to get it out of the serial buffer, which is part of how the Arduino decides whether or not it's time to send data to the Raspberry Pi. If we never take the character out of the serial buffer, it's always time to send new data because, well, there's always a character in the buffer. This is a count of how many times the rain buckets have tipped, rainfall in inches, the conversion factor for rain bucket tips to inches of rain. Similar to the rain counts, this is how many times the anemometer has rotated since the last time we asked for data. The conversion factor for 1 rotation per second equals 1.492 miles an hour. SparkFun just gives you that along with this rain constant. This will be where we store the average wind speed. I'll explain how the gust timer works when we get down to talking about the wind speed calculations. This here is also related to the speed of a gust of wind. We need to time every single rotation in order to find out, is this rotation the new fastest rotation? Gust wind speed in miles per hour, and then that's the reading from the analog to digital converter, which we use for direction. Remember those tolerances I talked about for the weather vane? Mm-hmm. This is all of those tolerances. So the low side, the high side, basically we do a check. If you are above the low tolerance and below the high tolerance, then it must be this one. Or if you're above this and below this, then it must be this, and so on down the list. The reason for doing these arrays is now we can do this check in one nice little for loop rather than if. It also makes it a lot easier to change one of these if we fail to detect a certain direction. So now we'll get into, that was all just sort of setup stuff, and actually I skipped some things. One is we need to include SPI because SPI is how the Bmp sensor communicates. These libraries here are for communicating with the Bmp sensor, and I forgot to put the comment in here showing where to get that code from. I'll just put that on screen when I'm editing this. And of course I'll actually add the comment so that if you want to download this program, then it'll already have that link. You can also add them through the library manager. Anyway, other stuff that I had skipped over was this. Various things from the Bmp example code. I don't think we actually need this, but the example code used it, so I've put it in as well. It's something for if you want to use the Bmp sensor as an altimeter. The tree should not be flying, so I don't think we need an altimeter. We need to specify the chip select pin for the Bmp sensor because, well, it's a requirement for SPI, but we're using hardware SPI, so MISO, MOSI, and the clock do not need to be specified. They are, well, the hardware pins. I've also specified the pins that we will use for the rain meter and the anemometer. Remember I mentioned that those need to be on interrupts so that the sensor can tell us when a rotation has been completed. Pins 2 and 3 on the Pro Mini happen to be interrupt pins. And then the last thing here is the analog to digital converter pin that we use for the weather vane. Last thing that I skipped over is creating the Bmp sensor object. All of this stuff that I'm talking about, the Bmp sensor, you can get that in the, once you install the library for that sensor, there's this example program that comes with it, which allows you to very easily check that your sensor is hooked up correctly and actually working properly. So, void setup, that just runs once when you turn the Arduino on. Open a serial port. This baud rate, I've set it for the fastest one the chip can handle, but you might need to go slower if you have long cables and you're getting errors. You can go as low as 300 baud, which is, it's approximately 300 over 8 characters. It's going to be a bit less than 40 characters per second. And if you're collecting data once every 10 minutes, that doesn't matter at all. That's plenty fast enough. So while not serial, just do nothing until the serial port becomes active. And once it's active, then we want to print the 2 lines which identify the Arduino program. And then the next thing we want to print is this line here, which shows it's the headers for the CSV file that you saw earlier. And if we can't find the Bmp sensor, say so. That's important. The only way that would...
Where does that message appear?
All of these get printed to the serial port. So actually, while you're working on this on the within the Arduino software, you can just open the Arduino serial monitor and, well, you can get data like this too. It just makes it really easy to test the fact that it's coming in over serial. Let's see, what's next? We need to set the rain meter pin and the anemometer pins as inputs, and more importantly, remember I mentioned pull-up resistors. We can do this and need a resistor in hardware, or we can do this and we don't need a hardware resistor because we're using the one built into the Arduino, the ATmega chip. This here explains some of the, explains the next 2 lines which make the interrupts actually work. So you have this attach interrupt function. You tell it what pin you want to attach an interrupt to, and you need this digital pin to interrupt function. You also need to tell it what function to call when the interrupt triggers, and we need to tell it the condition for which the interrupt triggers. And in this case, that's a falling edge rather than a rising edge or a change. That's what they call it, change. Okay, so the last thing to do as part of setup is to set up oversampling and filter for the Bmp sensor. Again, these are just straight out of the Bmp example code. And now we get into, actually I'll explain the 2 interrupt functions first, these 2. Increment rain counts is really simple. Rain counts plus plus, that's it. If the rain count interrupt triggers, all we do is make a note of the fact that the rain bucket has tipped, and that's through this here. Remember I mentioned the debouncing problem where the rain bucket would go back and forth once, but we would get multiple, and we would get multiple counts. This is where that issue occurs. So that's where the capacitor comes in. It makes it so that this interrupt triggers only once per tip of the rain buckets or per rotation of the anemometer. So now when we increment wind counts here is used for average wind speed, and it increments once per revolution of the anemometer. The other thing we need to do is figure out if the rotation that has just completed is the new fastest rotation. The way that works is, I think it's actually rather clever, and I don't remember the first place I found this, but the way this works is we have this variable that I called this rotation timer, which tracks how long the most recent rotation has taken. There's this function called milliseconds, and it just counts the amount of time in milliseconds that the Arduino has been running. And that's an unsigned long integer, so it counts up to 4.3 billion milliseconds before it rolls over, and that's just over 49 days. So rollover events are really infrequent, and if they're going to cause problems, the point is that those problems will be rare. But this code is special in that it is rollover safe, and if you're so inclined, I'll let you prove that for yourself. This millis always returns the current time. You can use that kind of as a clock. So milliseconds minus the last time that the interrupt triggered tells you how long the current rotation has taken. Now, the reason this describes the last time that the interrupt triggered is down here. This rotation timer equals milliseconds. So what we've done is we make it so that at the end of the loop, this rotation timer contains the time that a rotation was just completed. So now, maybe we've been sitting here for 5 minutes. Now we get to here. Milliseconds has increased by 5 minutes worth. I think that's 300,000 counts. And this is 300,000 counts less. Thus, this here ends up being 300,000. And that tells us that it took 5 minutes for the thing to go around once, and that's going to give you some very, very tiny rotation speed. Now we've figured out how long the last rotation took. Now we just check, is that the new shortest rotation? So if this rotation timer is less than the Gust timer, in other words, the new fastest, Gust timer equals this rotation timer. So now we've logged the fact that we have a new record rotation speed. Again, this stuff triggers every time the anemometer completes a rotation.
Is there anything that resets the Gust, the fastest time?
Yes.
Or does it go forever? All time fast.
We're just trying to get the highest wind speed of the last 2 minutes or whatever, 10 minutes. So the actually what happens is the Gust timer here gets reset to the just shy of 4.3 billion that we talked about before. And what that means is that we assume that it just will not occur. We assume that it's going to take 4.3 billion seconds to get to the milliseconds to get to the next complete rotation. And actually I can point that out in void loop. That happens down here, right after we calculate the Gust wind speed. I'll start up at the top of void loop because that'll make things make more sense. If serial available, in other words, if we've just received a character through the serial port, remember the Python or the Arduino serial monitor sends a character every once in a while. So if we've received a character, disable interrupts, and that's really important because we don't know how long all of this stuff is going to take to run. And because we don't know how long it's going to take to run, mainly we don't want to mess up the wind speed calculation. It's going to be a really small difference if it does get messed up, but we can avoid any errors completely just by disabling interrupts, so we do that. Timer equals milliseconds minus timer. That works exactly like it did for the Gust timer, except we have a different trigger condition this time. And in this case, the trigger condition is the if serial available. what we've done with this line of code is we have now calculated the amount of time that has elapsed since we were last asked for data. Down the bottom here, we have timer equals milliseconds, just like we had this rotation timer equals milliseconds. That's how we're tracking how much time has passed between requests for data. Now, if serial available, that will always evaluate to true unless we read the character out of the serial buffer and put it somewhere. So we don't actually need to do anything with that character. We just need to put it somewhere so that it's out of our way. Because if this thing, the easiest way to show you what happens is I'll comment that out, upload. Okay, so now what I've just done is, well, if I send a character, now it just spams us with data as fast as it possibly can, and that's not helpful. So we do absolutely need that, and I'll upload it again just so that we have the correct program on there. Now let's calculate how much rainfall has occurred since we last asked for data, and, well, just rain counts times the rain constant, and then print it to a precision of 3 decimal places because that's the precision of rain constant. There's no reason to print any more digits and give the impression of false precision, and there's no reason to throw away precision at this stage. So do 3 digits. We want this as a comma separated list of numbers, so print the comma, and then reset rain counts to 0. That way we're ready to count up how much rain falls over the next data collection period. So next we want to calculate the average wind speed in miles per hour and then print it. It works just like the rainfall except some different numbers, and because we have to do this division in order to get a rate, this was mildly annoying to figure out. It was just 0 forever, and it turns out that that's because these need to be converted to floats. Integer divided by integer, or integer divided by float, or something like that. It didn't work correctly. Next is the gust wind speed calculation, which is pretty much just like the average wind speed, and I noticed rather interestingly, it does not have the floats, but it works just fine. I am not sure why I have it that way, but it works. So after we do the gust calculation, instead of resetting the gust timer to 0, we reset it to the absolute maximum. In other words, we assume that there won't be any gusts. Now we get on to reading the weather vane, and the first thing we do is just read the ADC, analog to digital converter, and print that because I want to know what it actually measured. And the reason that's important is that this may not actually yield anything. This print statement may never execute. So there's 16 directions that we want to evaluate to. So we're going to iterate 0 up to less than equal to 16, because that's 16 items. Less than but not equal to 16. So 0 to 15 are the numbers that we actually count. And now we check if weather vane ADC counts is greater than the low tolerance and less than the high tolerance. Note that these are at whatever value of I we are currently on. If that evaluates to true, in other words, we're in the specified range, print wind direction I, and that is this list of stuff up here. However, if this never evaluates to true, in other words, we're never between this number and this number, or this number and this number, say for example we got a value of 69. 69 is between the high tolerance for east-southeast, and it's lower than the low tolerance of east-northeast. If that's where we were, all of the others, of course, would evaluate to false, but so would these, which means that
you don't know the wind direction.
Exactly. This line here will never execute, and we don't actually get a text name for the direction of where the wind is blowing. And we have to rely on this here in order to figure out what went wrong. So, like I said, this is basically just as a diagnostic tool for me so that I can sort of catch the weather vane if it's misbehaving. And then the comma to separate it. This bit here is also from the BMP example code. If not bmp.perform reading, what the example program did was it printed could not read Bmp Sensor. but there's two values that we want to print, and what I discovered is the simplest logic for this is it actually allows you to write to the bmp.pressure and bmp.temperature locations. Now, I could have it go in as text and have it be something like, well, I take that back. I cannot have it go in as text at this stage because bmp.pressure and bmp.temperature are floating point numbers. One nice thing about floating point numbers, the IEEE 754 format, is you can put a number, or you can have infinity, or you can have not a number. And 0.0 evaluates to not a 0 divided by 0 evaluates to not a number. So what I have done, I am having it use nan as a way of saying I couldn't get a reading. The very next thing is...
So on the wind speed one, why don't you have it just print unknown or something if it gets that value of 69 or something? Just UNK or something. Or
let's see. Yeah, I could do else, else unknown, but I would rather... actually, you give me an idea. Let's get rid of this. Now we're editing things while we're doing it. I'm actually just going to do it. Hang on. No. We can't just do else because this executes once per iteration of the loop. We would need to detect the fact that this never came true after we leave this for loop. That's why I did it the way I did. I'm not going to change it. Never mind. Okay, so if we fail to read the Bmp sensor, we set the Bmp readings to nan. That doesn't necessarily happen because typically we are going to actually successfully read that sensor. And if we read it successfully, the temperature and the pressure will print. And if they did not read successfully, for example, a bad connection or, I don't know, maybe water got into it and ruined something, in that case we will see nan as the temperature and pressure reading. And nan will be properly handled by any math code written in any language, so it's a way of having this error propagate through without needing to do anything fancy at all in order to track that the error occurred. And then the very last thing that we do, notice all of these are serial.print, and this last one is serial.println. The Python code that I'm about to show watches for that new line character in order to decide when the end of the data has occurred. So the last thing we do is print the timer, but we do it as println instead of just print. Now that we're done sending data, we can re-enable interrupts. We make a note of the time, the current time, and depending on your serial speed, that might actually be vastly different from the time up here when we decided how long has it been since we last collected data. Basically what we're doing is we're calculating how long has it been since we last collected data, but we completely ignore all of the time that it takes in order to actually collect the data. So it's truly just the interval between pieces of data, and we don't include any of the processing time. So that's all of the Arduino code, and this is onto the Python code, which receives data over serial from the Arduino.
And that's on the Raspberry Pi?
Yes, it'll run on the Raspberry Pi. Of course, right now it's running on my Mac. It actually can, if you can run Python, you can run this data logging code. And this is actually, in my opinion, pretty special code because it allows you to log any sort of data into the CSV format. This program just does not care whether you're logging voltages or weather or medical stuff. It doesn't matter. It's just recording it into a CSV file. So these are the modules that we need to import. Serial you actually need to download separately. Pip install PySerial is the command you need to run to do that, which you just go to your command prompt, type pip install PySerial, and PySerial will install. Of course, you have to do that after you've installed Python, otherwise you'll get an error about your computer doesn't know what pip is. Next is time, date time. Those are different. os.path and sys. os.path is needed for saving stuff. Sys is used for exactly one command, which I'll show in a minute. And This is perhaps the strangest line in the whole program, and yes, you do actually need to do it this way. From datetime, import datetime. Why couldn't we just have datetime as is? I don't know, but that's how it needs to be done. So the very first thing we do is we set up where we want to save the CSV data. Save location, OS path, join, system path 0. This refers to whatever folder you launched the Python program from. So in my case, this ends up being somewhere in my OneDrive folder. And then this is the name of the file that we want to append to the path. That's the whole os.path.join thing. So take the current path, append this to it, and now we have the full path of where we're going to save this file to. And then I have it print it to the screen just as a sanity check of sorts. The next thing we need to do is set up the serial port. So we have the name for the serial port. My Mac calls it this, and if you have a Mac, that name will change depending on exactly what USB serial converter you have. This command, if you're on anything Linux or Mac OS like, that'll tell you all of your devices, and the one you're looking for is probably something like /dev/tty USB 0, or if you're on a Mac, it's /dev. It'll have USB serial in the name or something like that. The names are not very consistent. And then on Windows, you don't need to do anything like this. Just look at Device Manager, and it'll be either COM1, COM2, and so on. Next thing we need to set up for the serial port is the baud rate. And it doesn't really matter what it is so long as it matches the Arduino and it's one of the standard baud rates. Again, you might need to use a slower baud rate than this absolute maximum if you're getting errors. And if you're getting errors, it'll be pretty obvious because actually the easy way to show it is to go to the Arduino program here, open the serial monitor, and select the wrong baud rate. And see, it's just complete nonsense. It probably won't look quite that bad, but you'll get garbage. It'll be obvious that you're getting the wrong data. So let's go back to the Python program here. We've set up the baud rate, data interval. That is how often we want to collect data. And at the moment I have it just set for once every 2 seconds because that makes it easy to debug things. Next thing is we need to set up a couple of functions. It just makes it easier to think about. We don't really need to do it as functions, but it makes it easier. So I have this function called getData, which basically it just reads the serial port, which we set up here, and trims the data to exactly the segment that we want. So read in the data with this serial.readline command. And when we read it in, it comes in as ASCII, in other words, 8 bits per character. Python natively works with Unicode, so I was rather amused to discover that Python now supports emojis. The emojis aren't the important part. The important part is that we need to decode this ASCII character array into a string of, not UTF-8, that's what we're coming from. We need to decode it into Unicode characters so that other Python functions can handle it normally. The other thing that we want to do is strip off a carriage return and a line feed. And Python has some really nifty notation for working with what they call lists or anything that's list-like. And this being essentially a list of characters, we want everything except the last 2 characters. Now what I have here, bracket, colon, -2 bracket, it's identical to this. So we're telling it start at 0 and go to length -2. It's the same thing. We're going from 0 until length -2, and that's the string that we actually want. We don't want those 2 extra return character type things on the end because they just mess up the rest of the formatting. Now we also want to append the date and time, so we add 1 more comma and then we add the date and time. And that's as 4-digit year, 2-digit month, 2-digit day, and then the time as 24-hour time rather than AM, PM kind of stuff. Then we print the data that we've just collected. That was how I was showing it on the command prompt, wherever that went. I think I closed it. after we print it, this print statement sort of inherently includes a return character. So we don't actually need another return character yet. After we print it, now we can put the return character back on that we took off at the beginning. The reason we had to take it off was so that this date and time ends up on the original line rather than on the next line. So now that we're ready for it, add the new line character and then return the data that we've just collected. There's also this function save data where, well, file equals open. We open a file at the save location that we set up here, and A for append instead of W for overwrite. Then we write the data and then we close the file in order to save it. So now we're almost down to the looping part of the program. We're out of defining functions and so forth. So with serial.serial, tell it the port name, the baud rate, and timeout is important because if we get no reply, we don't want this to take over the whole program execution. Actually, I don't really have it properly handling that error yet, but I'm not even sure I'm going to bother having it handle that error because I just don't know if that's worthwhile at this point. And the serial port will be called SEER, I guess. Yeah, that's just what we called it. So these 3 lines here, that will handle the first several lines that we get from the Arduino. We only need to handle them once, so we don't do it as part of the loop. And we want to handle them outright. We don't want them one line and then 10 minutes later the next line, 10 minutes later the next line. We want to handle all of those all at once, and then we want to handle getting data repeatedly. So first thing is we need to tell the Arduino, I want some data please. And we do that by sending any single ASCII character. So we're going with the question mark like I had talked about before. And B and then a character or characters in quotes, that tells Python do this as an array of ASCII characters rather than the native Unicode. So send a question mark to the Arduino, and then now that the Arduino knows we want data, Python needs to collect that data, save it, and then sleep for time or data interval seconds, and then do it all over again, and again, and again, until you tell it to stop. Now, another thing that isn't exactly implemented yet is I want this program to run on when the Raspberry Pi starts up. And that can be accomplished by basically dropping the Python script into a certain folder on the Raspberry Pi. And the Raspberry Pi just knows, okay, anything in this folder, start running it at startup, and just does it. So that's all of the code for this weather station. And
what happens if it runs for a very long time and the file gets really big? Can it get too full?
Well, you could fill up the SD card. However, if we're writing one line of data every 10 minutes, and let's find out exactly how long that one line of data actually is. Okay, so the easiest way to check that is just with a text editor like this. Okay, so it's 50 characters per, it's 50 characters per line. You're not going to be filling up any files anytime soon, especially if you're collecting only once every 10 minutes.
Okay.
So you're right, that is something to consider. And actually, I did think about that, but I thought about it more in the context of, do I really want to scroll through a file of 50,000 lines of data? Even if the file system's okay with it, I don't want to have to work with that. So I thought about trying to figure out how do you split off multiple files, and well, let's see. If we're doing it once every 10 minutes, well, we have 24 hours in a day times 60 minutes per hour, so it's 140 lines per day. Sorry, 144 lines per day times... No, we're doing it once every 10 minutes.
Oh.
So 1440 minutes, so... Yeah. And we're going to do it for, I don't know, a month. It's not even 5,000 lines. That's big, but it's not, like, unfathomable. And if you're using MATLAB to process it, which, if you're dealing with that much data, you're definitely into the realm of you should seriously consider MATLAB.
Okay.
That's no big deal at all. Now, if we're going to let that go for a whole year, I don't know, now I'm just playing with numbers. 52,000. So yeah, you're never going to run into a problem. And actually 52,000 times, what was it, 50? So it's going to be like, it's going to be like 3 megabytes after a year. You're not going to be filling this thing up anytime soon if you're collecting data at a reasonable rate. So that's all the stuff that has been completed for this weather station. There's a few things I would like to do in the future, or would like to see somebody do in the future. One is, the way the weather vane currently works is, whenever we ask for data, that's when it delivers the direction that the weather vane is pointing. Google the phrase circular average, and you'll find a Wikipedia article explaining what it means to take the average of essentially angles. If I have 5 degrees and 355 degrees, and you just average those, well, apparently the average direction is 180 degrees, in other words, south. But we know that between 5 degrees and 355, the average is actually north, 0, or 360, depending on how you want to look at it. And if you take this angle, convert it to Cartesian coordinates, average the x's, average the y's, you can correctly compute that the average direction is north. So that's one thing to implement for the future, something that calculates the average direction over the data collection interval. Let's see, there was at least one other thing that I was thinking about. Oh, another is that this set of sensors is not necessarily the final set of sensors. It's not necessarily the best set of sensors for our use case. It's just the sensors that were available on the devices that I chose to use, so here they are, implemented and working correctly. We don't really need to calculate rain accumulation. We don't really need to calculate the wind direction. We really only care about wind speed, temperature, and that's it.
Pressure?
Not really pressure, because pressure doesn't... temperature affects the efficiency of the solar panels. Wind speed affects whether the tree is going to be destroyed or not. And the last thing that cannot be measured with any sensor I've found yet, there are sensors for this, I just haven't found a good one yet. We would also want to measure light intensity, just as another reference point for how well are the solar panels working. If we're getting very low power generation, but the sensor says we were in full sunlight, what's going on? Well, probably one of the solar panels is dirty or something. And truly, if even one of the panels is dirty, the whole array goes down with it. So that's the weather station. That's a little bit more about the solar tree electrical setup, and that sure took a long time. But there we are, we're done.